Modern policymaking relies on a leap of faith. We take millions of interacting variables, economies, ecosystems, human populations, and condense them down into single numbers. We assume that if we measure an aggregate metric with extreme precision, we have all the information required to make a decision. If the top-line number is perfectly accurate, the logic goes, our resulting policy will be too. But a summary can be mathematically flawless and still completely erase the specific data needed for an intervention. Improving the statistical fit of a measurement does not recover the structural information that the very act of aggregation discarded. Once the data is compressed, the variance is gone. This is not a failure of data collection. It is a strict mathematical limit of mapping high-dimensional reality into low-dimensional summaries. Individually rational agents, or distinct microstates, do not automatically combine to behave like one representative macro entity. We see this structural breakdown clearly in two different fields. First, fisheries management, with inverse identification failures, and second, epidemiology, with intervention sufficiency failures. Despite the different domains, the underlying information problem is identical. Both suffer from mathematical collisions, where entirely different real-world states produce the exact same aggregate metric. Relying on a compressed metric without proving its structural limits mathematically guarantees eventual policy failure. This diagram outlines the basic catch per unit effort equation used in fisheries. The aggregate index I equals effective catchability, Q, multiplied by actual abundance, N. If actual abundance is 100 and catchability is 1, the model outputs a steady index of 100. Now, suppose the actual abundance plummets to 20, but fishing fleets become highly efficient, driving catchability up to 5. The aggregate output remains exactly 100. If both of those underlying states remain credible, the index alone cannot tell a manager which reality they are looking at. The single number hides a massive population variance. The northern cod collapse provides the empirical evidence for this mathematics. Because fleets targeted dense, localized schools, catch success stayed high, even as the actual stock and occupied area were actively declining. The aggregate metric remained accurate, and because of that accuracy, it actively blinded decision-makers to a cataclysmic systemic collapse. We see a different version of this failure in epidemiology. The basic reproduction number, R0, is calculated as the spectral radius of a next-generation operator. This diagram maps intervention paths from an aggregate R0 of 2.5. If a public health response uses uniform immunization across a population, the entire operator scales evenly. Here, the aggregate is perfectly sufficient to determine that herd immunity requires exactly 60% coverage. But look what happens under a targeted vaccine rollout. We can construct two distinct transmission networks that both yield the exact same R0 of 2.5. Despite sharing the exact same top-line metric, one network requires total coverage of 60% for local control, while the other requires only 33.3%. The R0 aggregate is operationally sufficient for a uniform target, but mathematically insufficient for a targeted one. The context of the intervention determines whether the summary is valid at all. To diagnose this across any discipline, we define three things: the underlying microstate, the reported aggregate, and the specific policy target. This visual represents the mapping process. The 3D plane is the complex microstate, projecting down to a single 1D aggregate line. If we select one value on that line, it projects a vertical column back up, intersecting multiple possible realities on the 3D plane. We call that vertical set of possibilities a fiber. Operational sufficiency exists if and only if the desired policy target is strictly constant across that entire vertical fiber. By measuring the spread between the most extreme target values on the fiber, we find its diameter. If two admissible worlds share the exact same aggregate metric, but output different target values, the diameter is non-zero. A collision exists, and the target simply cannot be recovered from the summary. Creating an aggregation map does not grant operational authority. Any variance on that fiber represents a strict mathematical barrier to safe decision-making. In practice, almost all macro aggregates will have a non-zero diameter on the fiber. Complete mathematical certainty is rare. This is where we apply minimax prediction and decision regret. We filter these mathematical collisions through the lens of actual consequences. A model can have target ambiguity and still yield zero decision regret. If every compatible macrostate on the fiber demands the exact same policy response, the ambiguity doesn't alter the outcome. The goal is not perfect identification. The goal is to mathematically guarantee that the maximum possible error stays strictly within the boundaries of the correct decision. This brings us to the formal repair protocol, the aggregation license. It is a versioned, revocable statement ensuring that one specific impression is safe for one target, population, and intervention. This chart tracks a synthetic CPUE workflow. An index of 100 with standard error margins yields an abundance interval anywhere between 79 and 131. Because this prediction radius crosses our critical action threshold, it results in a failure. The license forces us to augment the model with the least cost additional state. By integrating data from a single independent survey, the interval narrows to between 95 and 105. The error is now safely below the threshold, generating a pass. But the license also includes strict revocation clauses. If a held-out test introduces a sudden catchability shock, the CPUE and survey intervals become disjointed, instantly expiring the license. This protocol shifts model validation. Instead of resting on generic statistical fit, models must prove they operate within explicit, falsifiable boundaries of decision adequacy. This framework does not argue that all aggregation is invalid. We do not need to abandon representative agent models or macro indicators entirely. However, any narrow target diameter is only as reliable as the admissible state set and the identifying assumptions used to calculate it. Science and policy rely heavily on low-dimensional summaries to function, but we can no longer mathematically justify using metrics that hide the precise realities they are meant to govern.